All right, let's talk about the device you're watching this on right now. Your phone, your computer. Have you ever really thought about how it works? I mean, really, it's kind of wild when you think about it. Today, we're going to go on this amazing journey, all the way from a literal grain of sand to the incredible logic that makes all this possible. So let's get into it. Seriously, it feels like magic, right? You've got this glowing box. It's just metal, plastic, some glass, but it can do math faster than any human. It connects you to people across the planet. It lets you create art. But here's the kicker. Deep down, it's basically just a very, very cleverly arranged rock. So that's the big question, isn't it? How on earth do you make a rock think? Well, the answer is so simple it's almost hard to believe. All of it. The most sophisticated AI, the most beautiful video game, it all comes down to one single fundamental idea: a switch. A switch that can be on or it can be off. That's the whole secret. Let's break down how that's even possible. Okay, so let's start at the very beginning. How do we get from a boring old rock to a machine that can actually process information? It all begins with the raw material. The main thing in sand is an element called silicon. And silicon is special. It's what we call a semiconductor. Now, what that means is we have this incredible ability to control whether it lets electricity pass through it or not. And that property, that control, makes it the absolute perfect material for building our fundamental little switch. We're literally turning a piece of rock into the foundation of all modern tech. So, we've got our magic sand. Now what? Well, now we use it to build probably the single most important invention of the last century. And that is the transistor. Just think of it as a microscopic light switch. I mean, it's unbelievably tiny, but instead of flipping it with your finger, you flip it with a tiny zap of electricity. And it does one of two things. It either lets the current flow, which we call on, or it stops the current, which we call off. That's it. Your computer is made of billions, and I mean billions, of these little guys. Now, this is where things get really cool. We take those two states, on and off, and we give them meaning. We just decide that the off state means the number 0, and the on state means the number 1. And just like that, with a simple switch, we've created an alphabet. This two-symbol system is called binary, and it is the native language of every computer on the planet. And for decades, we got really, really good at making these things smaller. There was this famous observation called Moore's Law, which basically predicted we could double the number of transistors we could cram onto a chip every couple of years. This insane shrinking is why the phone in your pocket is literally millions of times more powerful than the massive computers that sent humanity to the moon. But that party is kind of slowing down. We've made these switches so tiny now, we're talking just a handful of atoms wide, that we're bumping right up against the weird rules of quantum physics. We're hitting a physical wall. So, okay, we have billions of tiny switches that can say 0 or 1. Great, but how does that become useful? How do you get them to actually do something? How do you teach them to make a decision? The trick is to arrange these transistors into little teams called logic gates. These are like the first level decision makers. They take in one or more of our zeros and ones, they apply a very simple rule, and then they spit out a single new 0 or 1 as the answer. Let's just take a super simple example. The AND gate. Its rule is dead simple. It will only output a 1 if its first input, input A, and its second input, input B, are both 1. In any other case, if either one is a 0, the output is a 0. It's a tiny, basic decision, but it's the very beginning of actual, well, logic. And here's the real leap. Once you have these simple decision makers, you can start stringing them together to do more complex stuff. For instance, if you combine a couple of different kinds of gates in the right way, you can build a circuit that can actually add two numbers together. And all of a sudden, wow, our little on-off switches are doing math. Okay, so our circuits are making decisions and doing basic math. But how do we represent really complex ideas like big numbers or letters or even colors using nothing but zeros and ones? For that, we got to talk about language. You and I, we think in a system called decimal or base 10. It's probably because we have 10 fingers, right? We use 10 symbols, 0 through 9. But computers with their on-off switches can only think in binary or base 2. They've only got two symbols to work with, 0 and 1. So let's look at a number, say 42. In our system, it's just 42. But to a computer, in its native binary language, it's this longer string of zeros and ones. And you can see right away, that binary string is a real pain for a human to read. It's long and confusing. And that's exactly why programmers came up with a shorthand called hexadecimal. which can represent that exact same number with just two characters, 2A. Now, this is a really important point. The computer doesn't understand hexadecimal, it only speaks binary. Hexadecimal is for us. It's a more compact, human friendly way to read and write the computer's language. And you see it everywhere once you start looking in error codes, in memory addresses, and even in the color codes that are telling your screen what colors to display right this second. Okay, it's time to put all the pieces together. Let's see how this whole system, these switches, gates, and numbers, actually creates the digital reality we use every single day. So, the simplest way a computer stores a number is in something called an unsigned integer. Just picture it as a fixed number of boxes or bits. If you're using an 8-bit system, that means you have a string of 8 zeros and ones. This gives you a specific, limited range of numbers you can possibly represent, starting from 0 up to some maximum. And for an 8-bit number, that maximum value happens to be 255. That's the biggest number you can make when all 8 of your switches are flipped to the on position. In binary, it's just 11111111. So here's a fun little thought experiment. The computer only has 8 spaces to store this number. What do you think happens when it's at its maximum value, 255, and we try to add one more to it? Where does it go? It just flips back to 0. It's wild. This is called an integer overflow. The best way to think about it is like one of those old school car odometers, When it hits 9999999, the next mile doesn't go to a million, it just clicks all the way back to all zeros. The computer does the exact same thing when it runs out of bits. And listen, this isn't just some quirky little fun fact. This is a huge deal. It's the source of some really famous and tricky bugs that programmers are constantly trying to avoid. And that, right there, is the whole story in a nutshell. We start with these incredibly simple on-off switches called transistors. We group those switches into logic gates so they can make basic decisions. We use the language of binary, zeros and ones, to communicate with those gates. And that whole system, layered on top of itself, is what allows your computer to do everything, from simple math to finding things in its memory to running every single piece of software you use. So the next time you pick up your phone or sit down at your computer, just take a second to remember this whole journey. You're not just using a tool, you're interacting with a universe of literally trillions of microscopic switches, all flipping on and off billions of times every single second, all of it built from a common rock. It's not about learning facts, it's about seeing through the layers. And that's a pretty cool superpower to have. Thanks for joining me.